Hello, welcome back. This will be the last section of Chapter 4. I know some of you are very happy to hear that. Um, in this last section, we're going to take all those things we've learned so far. We're going to learn how to write the empirical formula, the molecular formula, and then a structural formula for these simple molecules. And then we are going to determine the formulas of those using data from the lab. So we said empirical formula is the simplest whole number ratio of atoms, the elements in a compound. And we can determine the empirical formula by performing what's called an elemental analysis. And to perform an elemental analysis, we use something we call it a mass spec, okay? Mass spectrometer. And so we can actually combust those, burn them up, okay, decompose them, and then we can measure what the individual elements are that we're putting off. So the carbon and the hydrogen and the oxygen, this is really good for like organic things that are composed of carbon, hydrogen, and oxygen, because we can measure the CO2 coming off, the H2 coming off, and then we can back calculate into that, and then we can get the ratio. Now keep in mind, this is a molar ratio. It is not a mass ratio, because these things are together in mole ratios. Okay, so how many moles of carbon, how many moles of hydrogen, how many moles of oxygen. In order to know the mass ratios, we would have to go ahead and multiply those by their atomic masses. So, sorry. So these are the steps, and I like to give you like a summary slide so you can look at it. But the first thing you do is you convert the percentages to grams. So if it's 24.5% carbon, you know that is 24.6 grams per 100 grams. You convert any mass to moles. Okay, so then I'm going to do whatever to get that to moles. Then ever how many moles I have, I'm going to divide by the smallest. Because what I want is I want the ratio to be 1 to something. Okay, and so the way to do that is to whichever one's the smallest, I divide everybody by that, and then I'll get a ratio. Then if that's not a whole number, then I'm going to multiply that by something in order to make them whole numbers. Okay, you don't have to do this if you already get whole numbers, which some of your problems sometimes are set up that way. So for me, the best way, I'm kinesthetic, okay, so the best way for me to do it or learn it is to work a problem. So I don't know why I have a frog in my throat today. All right, so we're going to obtain the empirical formula from experimental data. And in this first one, I'm giving you how many grams of each thing we have. So we have 24.5 grams of nitrogen and 70 grams of oxygen. And we want to know what is the molar ratio of these, that is, how are they put together. Now this one didn't give me percent, okay, so I didn't have a percent. I've already got it in grams, so I can just start with these things that I've been given. So the 24.5 grams, I need to convert that to moles. There's 14 grams of nitrogen and 1 mole of nitrogen. Okay, and then I'm just gonna say equal, because I'm going to get a certain number of moles. And then I'm going to write this a little bit lower so I don't run out of room. Okay, and notice this is oxygen. It's not O2. Okay, it's the element of oxygen. And so 1 mole of oxygen is 16 grams of oxygen. And then I'm going to see what that is. So the oxygen is 4.38 and 1.75. So that's how many moles I have. Okay. And then I want to get this, instead of a ratio of 1.75 to 4.38, I want a ratio of 1 to something. So the smaller one is 1.75. So I'm going to divide them both by 1.75. That's going to give me 1 and 2.5. Okay, great. I'm getting closer. Unfortunately, I can't have 2.5 in a formula. It has to be a whole number. So then you ask yourself, what do I have to do in order to get those to be whole numbers? Well, if I multiply it by 2, that gives me a 5. If that hadn't worked, then I'd try multiplying it by 3, then by 4, then by whatever to see if I could get it, okay? This little chart shows you what you can do, but I'd usually just do 2 and then 3 and then 4 and then 5 if I can't do it in my head. Whatever I do to this one, though, I've got to be sure that I do it to this one as well. So I get 2 moles of nitrogen for every 5 moles of oxygen. So my formula, my empirical formula, is going to be N2O5. And that's the empirical formula of dinitrogen pentoxide. Okay, so you get grams first, convert it to moles, divide by the smallest number of moles you have, and then multiply by whatever you need to get it to a whole number. In this case, it was the 2. And never fear, you've got one. This one's got 3 different things, so you'll be finding out the moles and all that of a CHO compound. So that was without percentages. When you do have percentages, though, it's super easy. And the book does it a little bit different for me, but you know, the Dr. Kofelt way is going to be the easy way. So remember me telling you when you saw percent that you're going to automatically think if it's 60%, that's 60 grams out of 100 grams. And if it's 4.48 grams, it's percent, it's 4.48 grams out of 100 grams. And then 35.52 grams out of 100 grams. All right? Because that's what percent means. I can even just put a little equal sign there. So by doing that, I don't have to worry about writing anything else because I assume I have a 100-gram sample, then that's how many grams of each thing I have. So I have 60 grams of carbon, and I have 4.48 grams of hydrogen, and I have 35.52 grams of oxygen. And then what's the next step? I convert them to moles. So I've got to use, once again, the formula weight, or the molar mass. So there are 12 grams in 1 mole. Now, I've got to have 1 mole over 12 grams, remember, because I've got to have the grams cancel. So in each one of those, 1 mole of H is 1 gram of H. And again, if you want to do all of the decimal places, you can. Sometimes it'll make it come out closer. And then for oxygen, 1 mole of oxygen is 16 grams of oxygen. All right? And then I'm going to figure out how many moles of each thing I have. So I have 13.75 moles of carbon. I have, oh wait, sorry. I was looking at the wrong one. Oop. I don't know where my eraser is. Oh, there it was. Okay. Sorry about that. So that's 5. That's better. So 5 moles of carbon. You ever do that? Look and you look at the wrong place on the page. And 4.48 moles of hydrogen and 2.22 moles of oxygen. All right, so which one is the smallest? Because right here I'm going to divide by the smallest one, which happens to be the 2.22. So everybody gets divided by the smallest one. So this one's going to be 1. This one's going to be 2. And this one is going to be 2.25. So now I've got to figure out what do I multiply it by to get it to be a whole number. So I can look over here and it tells me it's 4. Or I could say, okay, if I multiply that by 2, that's 0.5. 3, that won't work. 4, okay, if I multiply it by 4, that's going to give me 9. So whatever I do to that one, I multiply everybody else by 4. So that gives me 8 and 4. So now all I have to do is write the formula, which is C9H8O. 4, right? Because I have to multiply that by 4. So 9, 8, and 4. So C9H8O4. And so that is my aspirin. And we saw aspirin earlier, and that actually is the same that we saw before. Okay? So again, this time you had percent. So you just convert that to grams. So we're assuming if we had 100 grams, that would mean we had 60 grams, 4.48 grams, and 35.52 grams. See how easy that makes the math. And so then you put it in there, change it to moles, then get it to the lowest, divide by the lowest one to get one of them to be 1. And then if you have to, sometimes these will be whole numbers already, and you just jump up and down. And like if it was like 7.925 or something, you can assume that is 8, okay? If it's more of a difference, I mean less of a difference than like 0.2, then you can round it, okay? All right. And so then we're going to do ibuprofen and show that that is the exact same thing with that. Okay, so those are the empirical formulas. Remember, the lowest whole number ratio. And so when you get the molecular formula of something, it's actually just a multiple of the empirical formula. In order to get the molecular formula, you have to know the empirical formula, and then you have to know what N is. And N is going to be your multiplier. And how do you know that? You've got to know the molar mass of the empirical formula, and then you divide the molecular mass of the molecular formula by the empirical formula, and that will give you your answer. So I have to tell you what the molar mass of it is in order for you to do this. Okay? All right, so let me show you what I mean. Butane-dione, very smelly, very nasty, contains carbon, hydrogen, and oxygen. The empirical formula for butane-dione is C2H3O. So that's the empirical formula. Its molar mass, the real molecule, has a molar mass of 86.09. So all I have to do is I'm going to compare the molar mass of my empirical formula to the molar mass of the molecular formula. So I do the same old song and dance I've been doing. I'm going to get the molar mass of the empirical formula. So I've got 2 and 3 and 1. So 2 times 12 is 24. 3 times 1 is 3. And 1 times 16 is 16. And so I add all of those up together, and I get approximately 43 grams per mole. So this is the molar mass of the empirical formula, This is the molar mass of what the actual molecular formula is. So what I do is I divide the big one by the little one because I want a whole number. So N equals 86.09 divided by 43, and that is 2. Okay, it's all over 2, right? Okay, 2.00 whatever, 2. So that tells me that my empirical formula of C2H3O, I'm going to multiply by 2 and get C4H6O2. Empirical formula, lowest whole number ratio, actual molecular formula, which is a multiple of that one. Of course, you have practice, and that'll be it. And so that is how you do the molecular formula from the empirical formula. So you've got a lot of skills that you learned in this chapter, and so they build, okay? So make sure that you master each section before you move on. Thanks for staying with me through the whole chapter.